Thank you very much, Tilos, for this warm welcome. And thank you all for coming. It's a delight to see so many of you here right now. You hear me clearly, right? Yeah, I see some nodding, so that's good. So who are we? Well, we are OMRT, and we call ourselves Future Makers, just like you. What we do, we actually want to digitalize the way architects and engineers work during design processes. And we, of course, going to elaborate about that, on that today some more. So, again, I am Jasper Spiegeler, background in architecture and civil engineering, did some programming and much Rhino and Grasshopper work during my studies.
And I'm Andreja Andrejevic. I did my bachelor's and master's here at this faculty. And I teach myself programming as well, like he did, and then we found each other.
So yes. Today we're going to talk about what we're doing, why we're doing this, and how we are doing this. And of course we're going to show you some example projects because we noticed that a lot of theory gets to be told at the university, but not much examples from practice. How does practice teach you, and what does happen there? And finally we're going to do kind of an interactive session, and maybe we'll skip one of the projects due to the time, but we'll figure out later together. Again, OMRT, what are we doing, and why are we doing this? Well, we call ourselves the digital engineer. So what is a digital engineer? I first want to tell you about how engineers now work in practice, and it basically goes from they ask from an architect before they have to do their calculations, can I have your PDF files of your project? So, okay, here you have my PDF files, and they manually go over the PDF file and check how much are the square meters, how much windows are in there, how do we calculate light, and they put it in an Excel, and there comes out one value, and they say if it's okay or not. So that's how practice deals with engineering stuff. We saw this, and again, we are familiar with rhinoceros and grasshoppers. So we basically want to translate these kinds of calculations into a much more digital design. And what brings that is that within these kinds of things, normally you have to have like 5 types of engineers, one doing the daylight, one doing ventilation, one doing another energy performance calculation. Now we have a program with algorithms that you can integrate, and you can calculate integrally all the calculations in once. So what am I talking about? A lot of stuff. This is our field of knowledge. Well, I would almost say these are like general fields of knowledge of engineers in architecture. You can see structural design, of course, a lot of building physics aspects, and of course also for the real estate investors, financial analysis. It's quite important. You see sustainability down there. It's more and more important. It's growing in importance. But again, to take you back a little bit, why did we start this? Because during the time, over time, we invented much more regulations for all these topics you just saw briefly. We invented more norms, more regulations, more guidelines to go through. And all these things have to come together into one design. So the architect, he has to be aware of so many things. But what happens is he needs an advisory by whatever party. It may be technical guys, financial guys, process-oriented guys that know a lot of things. And it all has to come together into one central, do you see the pointer? There, in one central design. But oftenly what happens is that there's too much miscommunication during the design process. And even so that around 10% of the building revenue budget of the Netherlands goes to failure costs due to these kinds of miscommunications. And 10%, to give you an idea, the whole revenue of the building cost is around 63 billion, miljard in Dutch. It's so 6 billion, if you have one solution for this all, you would directly earn 6 billion on your bank account. And that's where we see a future. what we're doing is this. Okay, so you can rewrite all these norms into kind of information technology stuff. You can rewrite them into algorithms. And what happens is suddenly you can integrally combine all these calculations into one systematic product. Because you see the market, I touched the word already, integral. It's kind of the new buzzword of the market, I would say. Everything has to go integral. And to step forward to BIM, which many of you probably know, building information modeling, it's already a kind of an integral process. But what we see is that it's only integral communication. One contractor draws like his ventilation pipelines, and the other one draws like the electricity lines. And what BIM does is it prevents from clashing. It's communication in 3D. But what's not yet integral is the knowledge itself of engineers. You still need a ventilation engineer, a daylight engineer, an energy performance engineer, a structural engineer. So we are aiming for integral knowledge that you can calculate in one 3D model in once. And what we're aiming for is the 6 billion, of course. Next. And what we see is that the market, it really leaves this whole digital transformation out. It just stays put. Like I told you before, the engineers still calculate things throughout PDF, Excel manually. But guys, we learn rhinoceros, right? We learn grasshopper here. We know about these stuff. And we see that the academics since maybe 2005 already write stuff about this, and it develops and it develops. So where is this development in the market? And at OMRT, we're trying to aim for this. We want to bring these developments into the market. To explain more about our vision, where it comes from, I think it's best to give the microphone, well, not literally to Andreja.
It's here. So yeah. So where did we come from? Where did we see all these insights and these problems in the market, and why are we aiming for advanced computing at universities since 2005, like Jasper said? It began actually when I organized in deze, maybe some of you know it, International Design Seminar here, and there we investigated the gap between the engineer and the architect, that it's evolved throughout the years where more knowledge of complex building was needed, so more engineers were born, but the architect still had the vision, and after a while they collapsed a bit. It was always the engineer that said it's not possible, and the architect that said he is raping my design. And we think the solution is in the computer. In computational design, in architecture, but in the built environment in general. And why is there such a difference, and why can the computer be of such importance to fill that gap between the architect and the engineer, that they get to know each other again and collaborate better? Well, this is an example we always show between the difference between parametric design and regular design. So parametric design is a part of computational design where you iterate through a lot of designs and can search throughout a lot of variants. Well, the difference is that with a regular design, it goes linear, and you have just one tool. If you use a computer very smartly, then you have a lot of tools, and you can put a lot of knowledge that you don't know by head, or you need a lot of people for, in an algorithm that tells you what happens, or that tells you if your design is going the right way or not. So like I told you, a regular design is when you design a couple of variants, and you just pick one and you test it. And you test it on, like Jasper said, all the aspects we're doing, so structure, facade, all types of building physics, sustainability. And for all those aspects, a lot of people are needed, but if one aspect doesn't work, you can start over again. So, well, in our opinion, not very smart. But what happens at the parametric way is that you start again with these 3 variants, but from out of that 3 variants, if one is a flaw, then there's still 2 other possibilities that give much more possibilities, and it grows exponentially in what your capabilities of your design are to a certain extent. You're in the end, as an architect, the one that decides which design is going to be, but it's not trial and error and go backwards, but trial, error, and a lot of more opportunities. And this is with this slide we show how the regular versus the parametric design process goes, in our opinion. The regular process is more of a waterfall method, where you just go from a concept design towards another design, and after a while the engineer comes and say, okay, this is good, this is bad, this is a, and it takes much time because you have to go back and forth and blah blah blah. But the parametric way, which is based on a bit of agile working, I would say, is that you continuously iterate through a lot of options, and the engineering does not happen at the end of the design, but in a very early design phase already. So you can know what happens with your design in a concept phase, engineering wise. So what happens with the daylight, what happens with the ventilation, what happens with the structure, and can do some very important decision making beforehand to prevent any design problems in the future. So, to know why our way of working is better, we have to show you what we exactly deliver then during a project before we go to the projects, the example project in practice. Is, well, Jasper told you already a lot of times, integral is a very important word. So what we do is we calculate integrally and give the solutions integrally. So they all have to meet each other. So for example, if you have a window in a design, in a 3D model, and you make it smaller, you see that less daylight is coming in a gradient, but at the same time you see how the structure behaves, but at the same time you see how flames can flash out in terms of fire safety. But they're all integrated with each other. So if one is not possible, the other ones aren't as well. So you have to always find a balance in the parametric design, and that's what the power of integrally means, that you always know which facet translates the other. So what happens when you can do integrated design? You can do a lot of variant studies. As I told you in the process, you have a lot of design options, but you can test even more and more and more, and well, you can iterate through thousands of design options based on any performance you want. Well, the opposite of generating a lot of design variants are optimizations, of course. You have one solution and you have a lot of design input. Go tell the computer, go find that one optimal solution for all the boundary conditions you've put. And last but not least, this one is very important, is that everything we do and everything we calculate and simulate is visual. So you can see how much daylight is coming in, you can see how fire flashes over, you can see how the structure behaves, you can see how ventilation goes through the building, which makes it very easy to talk with clients, say for us architects, real estate developers, and so forth. So from here, Jappie is going to explain you the first project in practice.
Yes, that's my nickname, Jappie. So, our first project, we call it O-Light. What does it? Why do we need it? Well, basically, we design the lights for sports fields. You won't expect that one, but apparently in the market, it's a huge market from Philips mostly, and the sports fields lights, what happens is you basically want to have a configuration of types of floodlights that shine their light onto the field, and you want a perfectly, well, equal lit field, literally lit. And nowadays, it's been calculated by a program called Calculus. It's written almost on MS-DOS. So all the lights you have to put in there yourself by coordinates. You have to define the field, its size, the dimensions. All dimensions you have to put in yourself manually. We build it, but then parametrically. So parametrically you can easily adjust the corner. You see like the dots. Those are the fixtures. I don't know where my own dot is, but you see the dots that are the fixtures, and you see the field. And if you put in another fixture, you see a completely different light equality on the field. This is, and just to show you, we benchmarked this program, our own program, to the actual one, and I think we're like 1% off. So it's quite valid. It's cool. But here you can see just some fixtures. We can calculate this in like 3 minutes. So next week we have a talk with Philips if they want to buy this from us or not. But in the end, what it's all about, it's not even the sports field, but it's also the surrounding. Because what happens, especially in the Netherlands, there's much more nuisance from light. You can maybe imagine that if you live somewhere and there's a sports field designed or built and you watch television and it shines bright in your face, you won't be happy. So now Philips does not only have the capability to make a perfect sports field, but also adjust the perfect sports field towards its surrounding. And this is bringing quality. This is bringing the actual quality for the market. So this is one example, and I'll directly give the clicker back to you. Next one.
As example. Another one which is, gives a very clear view of like the integrated simulations we do. As I told you before, this is a project. This is actually our office right now, so that's nice. We designed the facade for an office, but these are 9 stacked containers, and on the ground floor in the back there is a pepper sauce producer, and he was seeking space to grow his pepper plant. And the architect who was also in that building proposed, okay, we can maybe maybe design and create a double facade where you can grow the pepper plants, but it has to be an advantage for us. So they asked us and said, can you design and simulate and engineer the whole facade that the pepper plants can be of effect in winter and in summer to get most optimal comfort in the office. So we had a lot of variables actually and some parameters we had to test and see what would happen. So you have the double facade, you have the amount of plants in it, you have sun shading inside, you have the container doors which are still there, which can be of effect in terms of shade, for example. And you have the ventilation system you can play with. This is going to be natural, mechanically, in between, hybrid. So we tested this actually all out. So first we started with the ventilation test throughout the facade and see if we could reach an optimum of getting as divided as possible air through the whole double facade to get the plants, to give the plants a healthy environment. So this is where we linked flow design to Grasshopper to the whole model, and we optimized towards the one right below. It gives an acceleration at some points, but the best division over each compartment that gives enough ventilation for all the plants that could go in there. And then we used that information to calculate the heating of the facade itself, but also the impact of the heating or cooling of the facade towards the office behind it. So, meaning that it would be in winter a heat element and in summer a cooling element. And we wrote some protocol of how to actively work with the facade. So maybe close the windows and close the sun shading in summer and put the ventilation on 100% to get it cooled, and put even more plants in summer, and in winter vice versa, to make sure that in summer it's natural air conditioning, and in winter a true heating element. And with this project, which is really funny, it's now built. We are in there. There are not yet plants in it, but we're going to test if our simulations are similar to real-time tests we're going to make, and that's where we can validate our simulations as well. But this is one example where integration of different kinds of aspects are performance the design, let's say.
So the next one I will present again. This one is called Hyde Park. It's one of the largest building projects in the Netherlands right now, by Snippenprojecten BV. And they really had a high ambition on the amount of houses, or they want to build on the full area. And that makes it quite difficult. This is only one block of the 17 of those. So these are like, I would say, 120 households. And you can see that it's large. And they wanted from us to do the calculations by the normal building code regulations of daylight, because they were scared of or afraid about how much daylight would come in. And according to the building code, you can calculate a single house like this just without this adjacent building next to it, so it's next door building. While in reality, this is the next door building. It's 40 meters high with a street profile of 14 meters. So you can imagine that not much daylight comes into the lower ground floors of the building itself. But still, according to the building code, we could calculate it as if there was none next to it. But Snippen, they asked, okay guys, but we know there's not much coming in, and we want to have the good quality indoors. So can you calculate this? Well, okay, we will do that on a traditional way. That was the first question. This is the traditional way. You have to see how high, like, the upper side of the building is, and how much blockades there are for your own window. So you have to deduct some sort of equality factor that, okay, the window is this size, but actually only this small part there will be light coming through. That's what you calculate according to the code. And they actually didn't understand it, because we came out with two factors, one time with the building calculated next doors and one time without, and they just couldn't, they don't know, they're not technical people. So this comes, here comes the importance of visualization. We implemented a part of the model, you can see here, of the neighborhood inside our program, and there's the window we were calculating. And if you go to the next, you can see that, again, with or without the adjacent building and with, you can see that the amount of lux intruding is less. But now you can see it. And still, it's quite technical, so they couldn't quite get it. Like, okay, I see there's less, but how much less? And that's where we came in with the visualization. This one is really ugly because it's a really fast render, just to show you the intensity of the light. That goes from, again, without and with. But we also invited them to come to our office and do this all by VR. And that's where parametric part came in, because on the spot we could say, okay, how large do you want the windows to be? And they were walking through, and we put out the building next door. There was, well, quite some daylight coming in, but not much. And they could tell themselves, like, I want the window to be this size. And that made some value in the process.
Nice.
And I think we'll skip this one, right?
Well, we're a bit short of time. I don't know which one of you heard of Design Explorer? No, nobody?
Put up your hand.
Put up your hand. Oh, no, okay, yeah, nice. Nice.
From you, the record, by the way. Martijn, Nijkamp.
Yeah, okay, this is a way, we talked about visualizing our simulations and calculations, but also talking to the client, but also giving a way where all the integrated aspects come together and you can, be the decision maker in what all type of variants, how they react and how they perform actually towards what we calculated. And therefore I have this example. We show it oftenly because it's very clear, we think. We got a question by a real estate developer a while ago, and he asked us, can you, there's an area I want to invest in, I want to build 8 buildings. All buildings have a certain volume, we know that, but how is the area performing towards some comfort analysis and energy analysis? So he asked us, how much solar radiation on average comes into the area, what is the shadow nuisance of the buildings towards each other, what is the general shadow comfort and the comfort of a person on a terrace throughout the year, what is the amount of sun energy that's collected on the facades, and last but not least, a percentage of clear sight. So if you see a car here, I don't know where my pointer is, but there. If you drive towards the area, how much do I see? How much percentage of facades do I see that it's attracted to go there? And he said, okay, you can play with the positioning of the blocks, the form of the blocks, and the rotation of the blocks, but every block has a volume, a certain volume, and you have to keep to that volume. And he asked us, can you calculate the most ideal outcome? Can you optimize which composition works best towards all those parameters that were set? And we said, why would you optimize towards one, and then if you disagree, then optimize again? You have the same process in the end, and you just use the computer because it's nice. We said, let's iterate through all of them, 1024, and keep them, and make sure that we can discuss every single outcome, and that some of the outcomes are maybe better after a while or even worse after a while. And that looks like this. And this looks very complicated, but it's not. And Jasper is going to show you on the internet how we work with this and why it's so nice. So, the first thing the real estate developer asked when we showed this link, he said, okay, this is a bit intense, but can you show me all the compositions with the best score in solar energy on the facade? We said, okay, sure. And so this was the score, and he said, okay, this is not what I want, because the site percentage over there is very low, and he found that of more importance than gaining much solar energy. So we said, okay, well, let's put that up as well. And we saw that this is not a match. So, and he said, we asked him, what is more of importance, the site percentage of the solar energy that's collected on the facades? And he said, no, for sure the site percentage. So we dropped down the solar energy, and we came to well, design where you have a high side percentage and a bit less solar energy, and he agreed with this, and he thought, okay, this is nice, and he could play over other factors and see, well, what balance for him was the most smart and not for the computer. So with this we try to put in the human decision making, which is in our opinion very important. And you have a 3D model with it where you can show and hear all the results, and well, you can decide as a real estate developer that your side percentage is high, but somebody else says, well, the shadow comfort is a bit too low, and you can discuss well, towards the most optimal design amongst humans, I would say.
So this was our presentation for the Future Makers. Yes, wake up everyone. We hope you like it. And to close off, I think at OMRT we are always looking for really brilliant, bright, futuristic people. So I would invite you to, well, contact us if you are interested. And that was it.
Oh, not yet. If you want to get started with computational design, buy this book, then you get very smart in a couple of months. And also buy this one, because we wrote this one together with people on TU Delft here. So I hope you enjoyed it.
Thank you very much.